All right, now we're going to take our equation that we've been using, which is df equals I dl cross b, and we're going to use that to find sort of the force, or at least to estimate what the force on an individual charge q would be. So we know currents are made up basically of charges q, and we use conventional current, which suggests the charges are positive. So if you imagine n charges of charge q, and they're passing through a little line segment, say dl, in a time dt, how does that get us back to an actual equation for the force in terms of charge? So let's give that an attempt. Let me turn on my dot cam. So you can see I've drawn a diagram of basically a bunch of positive charges moving through a segment of wire. Let's say the length of the wire is dl, not unlike the dl that's here. So what we know is the current is a total of charge passing through an amount in a certain amount of time. So the current would be roughly N times Q over dt. That would actually be the current passing through the little segment of wire. But the problem is we can't really just, well, we can just stick that in there, and then we can use that maybe to relate it to Q. So if I plug this back into I dl cross B, I get df is equal to, keeping the vector quantity of it, N times Q times dl over dt. And of course, that'll be crossed with B. If I group the dl over dt over here, I think y'all can see that that would actually be velocity. So I'd get that df is actually equal to N times qv crossed with B, because dl dt is actually velocity. Now we want the charge, or the force on a single charge q, so we might as well divide that through by N, and we get that in fact this differential force df is just qv cross B. And since we're actually dealing with a single particle, we don't even need to call it df anymore. That takes into the account the nature that it's a very small amount of force, if you will. So we'll just call that F is equal to QV cross B. And this is actually part of the Lorentz force law, so we happen to know we're right. The Lorentz force law is basically this plus a term for combining or calculating what the total force on a charge Q would be if it was an electric and a magnetic field. So we end up getting the Lorentz force law, which I'll call F sub LF, is equal to Q times the electric field plus QV cross B. Now, as you can tell, we're focusing more on this part right now because I'm talking about the magnetism. We've already done F equals QE, but I just wanted you to know that that's the Lorentz force law. That's the Lorentz force law. So this one right here is F equals QV cross B. So how do we actually interpret that? Remember, cross products basically take two vectors and spit out a third vector, and that third vector has a magnitude equal to the product of the magnitudes of the vectors. So the magnitude of QV times the magnitude of B multiplied by the sine of the angle between them. Of course, we can use that just to find the size, and then we can find a unit vector in the direction that it actually points and multiply those two, and we actually have the force as a vector. How do we find the actual direction? Again, we've got a cross product, so we're going to use the right-hand rule. So if this were the first vector, and it is the first vector in a cross product, you know, I normally align my pinky along the vector QV. So if the charge is positive, QV is the same direction as V. Remember, if you multiply a scalar times a vector, you just get a vector that's parallel to the original vector unless the scalar is less than 0. So if it's positive, you just get a resized vector by multiplying it by a scalar q. If the q is less than 1, you get a smaller vector. If the q is greater than 1, you get a bigger vector. But if the vector is, or excuse me, if the scalar is actually negative, then you get a flip around. So what I do is I always consider, am I dealing with positive particles or negative particles? Okay, if I'm dealing with positive particles, then I lay my pinky right along the vector v. If I'm dealing with negative particles, I put my pinky the opposite direction. In other words, I point it in the opposite direction of v. And then again, I roll my hand until my palm can actually curl, is in a position where my fingers are allowed to curl towards the v vector. Or again, you can use this, where this is the QV vector, which is parallel to V in a positive case, or anti-parallel to V in a negative case. This is B, the middle finger here, and then the thumb, which is mutually perpendicular to both, is the direction of the force. So on a simple case, like if you have, let's say a charged particle that has a positive charge Q with a velocity V moving to the right, and let's say a magnetic field B pointing up, I could take and put my fingers like that. Since Q is positive, QV is parallel to V. So I do that. I put my finger in the point of V, and that would actually force this charge to move up. In other words, you'd feel a force pointing straight up, according to my right hand rule this way, or according to my right hand rule this way. So that's actually how a charge is affected by a magnetic field. Notice if the velocity is actually zero, then there's nothing, no effect, no force on the actual charge. And notice also that the force turns out to be a force that's both perpendicular to the velocity and perpendicular to the B. So you get some neat things. In other words, you see a B vector pointing one way, you see a V pointing, a velocity vector pointing another way, and you get a force in yet a third direction. That's just sort of counterintuitive to what we're used to seeing. We're used to seeing forces parallel to velocity or maybe perpendicular to velocity in the case of a circular motion or so on and so forth. So that is how this equation actually works. If you wanted to, for instance, consider the force on an electron moving with a speed of, let's say, 400 meters per second, we'd say F is equal to QV cross B, but magnitude-wise, it's just F is equal to QVB sine of the angle between them. Again, QV being a vector and B being a vector. Put them tail to tail. The angle theta is the angle between them when they're tail to tail. So we take an electron charge, that's 1.602 times 10 to the negative 19th coulombs. Let's say it's moving at 400 meters per second. And that the magnetic field is 1 Tesla. And let's say they're perfectly perpendicular to one another, so sine of 90 degrees just becomes 1. So in that case, you just get a 1.602 times 10 to the negative 19th times 400 times 1, and you get 6.40 times 10 to the negative 17th, or 6.41. 10 to the negative 17th newtons. So again, this just reminds you what the charge of the electron is. For instance, of course, it would be negative, so we'd actually have to treat it a little differently here. So in this diagram, for instance, if this were the electron moving, we would in fact say QV points this way, and then B points that other way. So we actually have to move our finger like this, and then we'd see that the electron would actually be forced to move into the page. It would have a force pointing into the page. Notice the velocity was this way, so it's going to tend to be perpendicular to it at all points. It's going to tend to make a circle. I hope that gives you a little help on how to deal with forces on charged particles.